Hey folks, and welcome to Advent of Code in F Sharp, day 9 already. Oh, time sure flies. Um, Yesterday we left off on day 8, and I was this close to solving it, but I had to go to work, so let me quickly catch up. Ooh, I look tired. Again, 6 o'clock in the morning for me. Let maybe adjust the cam a bit. There we go. So, um, I was working on day 8, but could not finish it on time. I have finished it in the meantime, and I was actually overdoing it a bit. So, as a quick reminder, I was figuring out for every of the 7 segments in this LED display, I was trying to figure out which was which. But apparently, you don't even need to do this. The um, the problem just asks you to figure out which configuration is which digit. And what I was trying to do was like way beyond that. I was trying to figure out every segment individually. So once that hit, uh, I did not change my strategy at all. I just do less. So these are the 4 easy numbers from part 1. Oh yeah, someone asked me to bump the font size a bit to make it more readable on small screens. So let's do that. Is this more readable? I hope so. So these are the 4 easy digits because they have unique segment lengths. And then for the rest, there's actually 2 groups. There's one group of 5 length segments or digits with 5 segments. There's another group with 6. And if you just grab a couple of those segments, for example, from the numbers 1 and 4, for the number 1, I grab the CF segment, like set containing those two. And if you know those two, you can take a look at the number 4 and grab the BD segment. That's like the this corner here. If you have those segments and you start to look at the individual buckets of like all the digits with 5 segments, you can start to deduce every digit, which is what I do here. For example, grab all the segments of length 5, then you know the 3 is the one in that bucket of 5 number segments, which has the CF segment, like the 1 in there, because the other ones don't, and stuff like that. And if you do this for the 2 buckets of 5 and 6 segments, you get all the different configurations for the different digits. And then that's something I was not doing yet on stream yesterday. I just build a map saying like this configuration actually that represents the digit 0, and I do that for all 10 digits. And then it's just a matter of looking up every configuration in the output, so the right hand side of this thing, to transform back to digits, and then we just sum them up. So all in all, I was struggling really bad with day 8, but I think it might just be my favorite puzzle of the year up until now. Really interesting puzzle to solve. I see we are nearing the deadline for today. I'm going to get rid of this beautiful drawing I made. There we go. Did I? Yeah, I have my notes with me. There we go. Just gonna set up my note-taking app because we are entering puzzles that I can't solve by head anymore. I like to draw things when I'm stuck, so just setting that up. Let's make sure that it is set up. It's maybe a bit white. There we go. In the meantime, let's open up day 9. Oh, that looks like a small one. Is this working? No. Yeah, it is actually. I just need to select the pen. Yeah, there we go. Okay, so I can draw if I want to. That's good enough. Day 9, smoke basin. These caves seem to be lava tubes. I have not heard of lava tubes. A natural conduit formed by flowing lava from a volcanic vent that moves beneath the hardened surface of lava flow. If it empties, it will leave a cave. That is so cool. Oh wow, I had not heard about these phenomenons yet. Cool. Parts are even still volcanically active. Small hydrothermal vents release smoke into the caves that slowly settle like rain. If you can model how the smoke flows through the caves, you might be able to avoid it and be that much safer. The volcanic thing is like super actual, no? The submarine generates a height map of the floor of the nearby caves for you. So it's a height map of the floor. Smoke flows to the lowest point of the area it's in. For example, consider the following height map. Each number corresponds to the height of a particular location, where 9 is highest and 0 is lowest. Yep. Your first goal is to find the low points, locations that are lower than any of its adjacent locations. Most locations have 4 adjacent. Locations on the edge or corner have 3 or 2. Yeah. In the above example, there are 4 low points. Oh yeah, so those are the points that have higher neighbors, and we are not doing diagonals. Cool. All other locations on a height map have some lower adjacent locations and so are not low points. The risk level of a low point is 1 plus its height. In the above example, risk levels are whatever, and then we sum them. Find all of the low points on your map. What is the sum of the risk levels of all low points? Yeah, we're finally doing 2D stuff. I was waiting on it for to show up. I have not used my 2D grid skills this year, I think. Let us grab the input and let's take a look at how big it is. It's pretty big. Nothing we cannot handle. Let's make sure we have day 9 opened up. Let's also grab the example. Yeah. My general approach when I see stuff like this, where we have to do game of life style problems, where looking at neighbors is important, stuff like that, I always grab a map data structure because it makes it really fast to look up neighbors. It's like a constant operation, or no, not constant, logarithmic operation to figure out all neighbors for a given point. So we're going to use 2 things, xy coordinates to represent the position. We can just do that as a tuple, and a map to represent the entire grid. Mapping positions to the numbers. So let's parse this into a map of mapping coordinates to the numbers. All numbers are single digit, yeah, of course. So let's give it a try. Let's parse. I'm just gonna try it in the REPL first because before I write any kind of function. So we have a list of strings. So let's map over that. Do we need the indices? Yes, we need the indices. So let's use a map index. So we have an index, and it takes a function that takes the index in an element. So let's write parse line. And we need to loop over every element in the line. Well, let's write a for comprehension. Looping, it looks clean with a for comprehension as well. So how do you do that again? Is it a for I in? Yeah, okay. So for digit in line, let's parse the digits. We also need the column number, so let's also index that. So it is for every column and digit in line, we return the row, index. Let's rename that in a second, and a column. So that's the key, and the value is the integer parse of the digit in that location. Yeah, I don't like index here. Let's call that row. row XY coordinates will go like from the top left down and to the right. So X is for most of these problems I take X to be the row which goes down. That's actually really weird to look at it, but it doesn't really matter for this. So probably this works. No, sequence int is not compatible with a string. That is true, but why do you expect the what? So line is a string. Let's explicitly type that. Type inference is awesome until it doesn't work. Okay, it does work. Let me quickly pull up chat so I can see chat. Okay. Yeah, so that works probably without the string and type annotation as well. It does. Now that I see this, do I like it? Do I want to write like a nested list comprehension instead? Yeah, it makes more sense. The map I and then the index, it's not symmetrical enough for my tastes. Let's do that. So instead of a single for comprehension, let's do a nested one. So this is example, and we index that as well, and we do the nested comprehension. We only need one list, we don't need to nest them because we will plop them together. And we let's do parse input, and then let's try to parse the example again. That should give us a list of every element with its coordinates. 0, 50. What? 0, 0, 50? 0, 149. I'm not doing what I think I'm doing. If you parse a character to an int, what happens? So let's say int a of 1. Yeah, that's not what we want. So let's do real parse. We could use the C# or the .NET parse. What is it? System.int32.parse, but we can just do this slightly dirty thing and go around to the string world. And then I think you can parse a string into an int using that int function. 2, 0, yeah, that works better. So now we have the full list of elements. Let's put that in a lookup table or a map. How do we call this thing? What does the exercise call it? Height map. Let's call it a height map. Height map, height map. Let's maybe make that explicit as a type so people can read it without having to open an IDE. So a height map is actually a map mapping coordinates in the 2D plane. So that's an int tuple to a number. And let's have parse return this. It's really clear what we're doing. Should still work. Yes, let's try to parse the input as well. Cool. Do we have a 8 in the top left? We do. Okay, I trust this enough to continue. So we have our grid. What's next? For part 1, we need to find the low points. Low points, yeah, that's what we call it. So in theory, if we loop over every element in the height map and we look up the neighbors, if it's the lowest point of those points, we have a low point. Yeah, so let's loop over all the points. Can I Yeah, for this loop, we'll have to drop down to. Oh no, I think we have something new in F#6. I think we have a map dot keys and a map dot values. Is that correct? We have a map dot keys. It's a collection of keys. Yes. So we used to have this in C# world forever. This is, I think, a recent addition to the F# API. Let's try it out then. See what it gives us. I'm not gonna bother writing an abstract data type or writing like functions. I'm just gonna let the it's a map detail leak through today. Whoa, I collection. I don't know if I like I collection actually. Okay, it's just a sequence. It's just an enumerable. That'll work. So we have to loop over every single one of those and look up the neighbors. That's maybe a good first step. That's a good first step. Should we looping over locations that I don't mind? Looking up neighbors that could use a refresher. So let's try that first. What would that look like? Find neighbors. Given a height map and a location. Let's first figure out the locations of those neighbors. So we just twiddle the x coordinate, one up, one down, and we do the same for the y coordinate. So it's and we don't do diagonal. So it's just something in the lines of, hey, go back in x and go up in x. Also do this for the y. Let's also do it minus first. And let's go forward in y. And for these 4 locations, let's map that. So we apply these deltas or these twiddles, these little tweaks to the location. So let's destructure this into x and y coordinates as well. So if we apply the delta on x and the delta on y, I think these are the coordinates of the 1, 2, 3, 4 neighbors. Yes. We potentially have like elements in the corner, and they don't have those 4. They just have 2, and there's some with 3. So not all of these coordinates will always map to a valid location on the grid. But I'm just going to let the map data structure take care of that for us. So we map over those neighbor locations one more time. And then we just say, okay, map, try to find me this location. Yeah, that gives us a list of options, and if we don't find the element in the map, we get a none back. We don't really want to stay in that option world. We just want a list of all the neighbors. So there is I think a choose function. Yeah, a choose function gets a function that maps an element to option, and it returns a sequence of t. So a sequence of u, sorry. And it literally does what we want. If it's like a sum value, it keeps that element. If it's a non-value, it just throws that away. So this list will actually only contain valid neighbors, I think. So let's just try that out. How can we try that out? Should we build a smaller map? No, I'm just gonna try it out. Yeah, let's just try it out. So let's map locations. And let's map a find neighbors over it, given the map itself. and that location. So this should map every location to its neighbors. Let's maybe also keep track of the position we are handling. So we have both the position itself and the neighbors. That's not what I want to do. I don't want functions, I want values. Yeah, that's better. Oh yeah, first is location and the second is just the values at the neighboring locations. That's confusing, but okay. So first location should have a 9 and a 7 as a neighbor. No, that's totally not what I'm seeing here. Am I using the example? That's better. 3 and a 1. That is what I expect. Yeah, that's what I expect. I think we are almost done for part 1. I don't like the keys thing already. I'm just gonna grab tuples. So that is location and value. And let's map the value, or let's return the value and height map our neighbors at that location. I think that will be more readable and more suitable for part 1. Let's call this locations with neighbors. Come on, fingers, wake up. Do we have what it takes? We have what it takes. So 2 has 3 and 1 as a neighbor. 1 has 9, 2, and 9. Yeah, that looks correct. Maybe let's... No, that's not better. Let's keep it a bit ugly. Yeah, and now we just want to find the lowest points. Do we call it low points? Yes, we call it low points. Let's find low points. Those are low points where the first element in this tuple is lower. Can it be equal? No, it have to be lower than any of its adjacent locations. So it has to be smaller than anything in the second part of the tuple. So that sounds like a filter. And let's write a isLowPoint function, which takes value and neighbor values. And it returns a boolean. Yeah. Let's just do a min on the list and return, hey, is value less than that minimum? Then we have a low point. So that should already give us something. Yeah, that gives us 1, 2, 3, 4. A 1, a 0, a 5, and a 5. Is that correct? Oh, 1 and a 0, a 5, and a 5. Yeah. That's good enough. This name does not make sense because we're doing more. We have low points, so let's map them. So we only have low points. We don't need the other craft. Yep. And then we need to calculate the risk level. Which is a bit stupid because it's +1, right? Two 166, that is correct. Then we need to sum those. And that's the solution. There we go. So for our example, that should give us 15. 15 is correct for our input. Let's Sparse the input and run it. Gives us a different number. Yay, that is correct. I'm happy. I'm not gonna put stuff in functions. It's additive code. We're here to solve puzzles and have fun. Let's take a look at part 2. What do they want for part 2? Next, you need to find the largest basins so you know what areas are most important to avoid. A basin is all locations that eventually flow downward to a single low point. Yeah? Therefore, every low point has a basin, although some basins are very small. Locations of height 9 do not count as being in any basin, and all other locations will always be part of exactly one basin. So yeah, we're clustering into basins. The size of a basin has the number of locations within, yep, including the low point. That's an interesting problem. It's reminding me of the Dijkstra algorithm. Like the way they thought the Dijkstra to me was with a paint bucket. You drop a paint bucket on the floor and the paint starts to spread slowly. Yeah, it's a graph algorithm. I think we can apply that here. So we just drop paint buckets on every low point and every tick that pool spread, and that's part of the basin. I think we can do something like that here. So in this case, that would... what am I saying? We need to take the height into account, not just distance. How would that work? So 1 was the low point, right? Yeah, 1 is the low point. So before the buckets of paint or the pool of paint can spread, they need to take a look at heights. We could... Does it always have to go up by 1? It's like 5, no, 5, 8. We can do that as well. But that only happens... I think we can do a Dijkstra-like algorithm, but represent like the height as well. So the first stick you can that the paint can climb. That's not... The metaphor is not making sense when you take height into account, but the paint is like pooling and we just keep throwing in paint, and in the first stick it can flood over to like 1 elevation higher to a 6, and then a tick later it can flood from everything we have up until that point to 1 higher, which is a 7, and then we can flood to 8s. I think we should be able to Dijkstra with elevation. Or at least in my head, it makes sense. Yeah, what I'm seeing here now is that the nines, there was something about the 9s. Oh, they are not in any basin. They reach the top. So I think from every low point, we can start running a Dijkstra plus elevation algorithm. And just take that low point number and increase that for a few times until we like reach a 9, and then we are done with that basin. Will that work? What happens if we have 2 adjacent basins that are not separated by a 9 wall? Yeah, we do need, I think, to run the Dijkstra algorithm in parallel or simultaneously for all low points, so we cover that case. So the first pool that hits a spot, starting from a specific low point, that is the basin that the point belongs to, not others that might reach that point later. Yeah, I think Dijkstra is still a good fit for this. It's been a while since I had to do stuff like this. So let's see how well it goes. We're already 30 minutes in. What do we need to change? We still need the low points. Yeah, we still need low points. So I'm gonna grab those. That's this part. Risk levels. We don't really need risk levels anymore. Let's use the example instead. I'm gonna get rid of this test stuff. If you want to test stuff in the future, I'll grab it again. Okay, the low points. We need actually we need the location and the value for a low point, right? It makes more sense to have locations than values in this case. So find neighbors gives us the neighbors value. So yeah, let's keep track of everything instead of just the value. Then our is low point probably changes as well. Yep. So let's do a lambda here. Which is what does this thing return again? Log value and neighbors. That also already looks not that pleasant to the eye. It's not really a pleasing line of code. So is low point takes the value and neighbors. And that's enough. I'm gonna get rid of this tuple syntax. Makes no sense anymore. So let's get rid of that here as well. We don't need the location for filtering. Cool. So that's the low points and their neighbors. Do we need the neighbors? We need the neighbors, but we need them for Dextra. We need the values and the locations as well. So actually, everything changes a bit. Yeah, here we do map, try, find. Here we do map, try, find, but that gives us the value. We would also like the location, right? Yes, we need the locations. No, we don't. No, we don't. For Dextra, we just need the values as well. But we do need to start marking stuff. How will we do that? Anyway, let's just proceed as planned. Let's not even worry about the neighbors. That's part of the Dextra algorithm. Yeah, it's part of the Dextra algorithm. Let's just keep track of the low points themselves first. We need those before we can do anything else. These are the low points. 1055, yeah. Okay, now we Dextra. Is the paint bucket metaphor on there? Or do we have to call my professor from ages gone by? No, it looks like it's something my professor came up with. Really? It's a good metaphor. It made sense. Yeah. So let's not use the paint bucket metaphor. No one will understand this. Let's just do let's call them edges, nodes, weights, distances, stuff like that. I think I'm saying like it's Dextra plus elevation, but I think if we interpret the concept of distance differently, it's just plain old Dextra. And even like this animation, these walls, nines are walls, and instead of having always a distance of 1, the distance is just the difference in elevation between 2 points. Mark all nodes unvisited. How will we do that? Maybe I'm thinking instead of like keeping boolean markers or boolean flags, we could just keep a set or whatever. Yeah, a set of locations, and that's like the unvisited set. And every time we visit a node, we just remove it from that set. I'm thinking, will there be cases where a point is like part of 2 basins at the same time, like they're identically or just as fast? I don't think we have to take care of that edge case, right? No. Every low point has a basin. Can we interpret this as there's only 1 basin for every point? Dangerous assumption, but I don't see. Yeah, it could happen that we have like a basin with 2 identical low points. Nah, let's not take that into account. Oh, there we go. All other locations will always be part of exactly 1 basin. So that is an edge case that we don't even have to consider. Okay, the algorithm is forming in my head. So let's... we have the low points. We need we need a set of unmarked or unvisited locations. Yeah. We are going to have to do some recursion on this part, but let's first do a single step and see if it makes sense. That's the whole thing. So that's all the locations we have in the world except the low points. No? Low points is a sequence of locations and values. Yeah. Do we need the values there already? You know what? No. We can look up a value in the grid whenever we want. I'm just gonna keep track of locations, not the values here. That's going to be a bit more easy. Is it? Yeah, it is. We'll clean this up later. Just now I want to have it compiled. So these are the locations. I hope these are the locations, at least 0, 1, 1, 9, 2, 2, 4, 6. Yeah. So now we have all the unvisited locations. I'm going to do a quick check. So how many low points did we have? I think 4. Yeah, how many points do we have in the height map? 50. Yeah, could be the case. This should be 50 minus 4. Yeah, that's correct. Okay, I'm comfortable enough to proceed. This is probably correct. So now we can do a single step of the Dijkstra algorithm. What is the first step? It's just taking a look at all the basins we have right now. Let's maybe read Dijkstra first. So we have marked all unvisited nodes, or every node is unvisited at the start. The unvisited set, actually it makes sense to... it makes sense to model that as a set as well. That's something for later. Assign to every node a tentative distance value. Tentative distance. Is that the infinity thing? Yeah, I remember it vaguely. So every node has a tentative distance. Set it to 0 for initial node. So for all our low points. Oh yeah, that's true. We're not doing just Dijkstra. We're doing Dijkstra for every low point. So low points have a distance of 0 because they have a distance of 0 from the point itself. That makes sense. Tentative distance of a node is the length of the shortest path discovered so far between that node and a low point. So instead of just the distance, I think it might make sense if we keep track of tentative distance per low point. That sounds already complicated. Do we need to do that? Yeah, we need to do that. Or actually, no, we don't need to do that. If we... Yes, we definitely do need to do that. I'm just thinking, so from the second that we reach a point, or based in X, say, we know it's the shortest, right? Because otherwise another low point basin would have touched upon that location beforehand. I think so. Since initially no path is known to any other vertex than the source itself, which is path of length 0, all other tentative distances are initially set to infinity. Set the initial node as current. The only thing that is tripping me up is in the original Dijkstra algorithm, we're doing a search starting from one node, but we are kind of doing a search from multiple low points. So for the current node, consider all of its unvisited neighbors and calculate their tentative distances. I'm gonna take Dijkstra as inspiration. I'm not gonna do a literal Dijkstra. So we're just gonna do the pooling of paint or of lava, whatever metaphor. So we just grab all low points and we start growing a pool of something. And every location that the pool hits first, that's part of that basin, and that we can remove from the unvisited set. In theory, that works, right? Yeah, let's do it that way. So instead of visited nodes, unvisited nodes, let's just keep track of the basins, which is the bigger collection. And let's try to fill that with some sort of liquid. In my head, it's making sense, but I'm having a bit of trouble translating this idea into code. So we have low points and we have a set of unvisited values. Okay, and every low point is like a mini basin, and we need to pool those basins. So we have to kind of loop over low points, or do we need to loop over unvisited? I'm gonna loop over low points because I want those to grow until they cannot anymore. The halting condition, or when do we stop? When unvisited only contains 9s? Or can we just get rid of the 9s altogether? In my head, it makes sense to get rid of the all the 9 values. Does it make sense? Do we need to know them? Those are like hard walls where a basin stops. But if we just get rid of those nodes, I'm not sure. So let's keep them in until we bump it against them. But in any case, I'm not gonna think about the algorithm too much. I'm just gonna like figure out one step of the algorithm in my REPL, in my interactive window, until I see the pattern. So we have low points here. Let's do something for every low point. Let's try to grow that pool, or that basin, that tiny mini basin, into a bigger basin. So instead of treating it as a list of points, I want to start treating this as a list of basins, and let's make a basin a list itself. So if you do a list singleton, those are now suddenly lists, right? Yes. Let's not do that here because we need that to calculate unvisited. So let's call this thing basins, and that's the low points. But hey, every low point is itself a basin. What? That's 1, 2, 3. That's one too many. What's happening? Oh yeah, that's because I was playing around with it in the REPL. That's better. So these are all the basins we start with. And let's start growing every basin. I'm just gonna grab just the one to make sense again in my head. We'll do the looping part later. So we have a basin. Let's try to grow this basin. No, we do need to do it for all the basins at the same time. Do we? Yeah, no. It is the elevation part that's making it hard for me. Yeah, I'm gonna need to do some drawing. Let's grab this beautiful example again with my old trusty snipping tool. So we can doodle on it a bit. So we have low points. Currently, they're all like mini basins. And the thing we're trying to do now is grow those basins. So what do we do? For every like iteration, so for every, yeah, let's call that an iteration, we take a look at the neighbors of every current basin. And a basin is a list of points again. So we have to do that for multiple possible locations. And we say, hey, let's figure out the neighbors. And that would be, oh, that's a very big blue dot. Let's make it a bit smaller. We say that, for example, there's 0 low point. Hey, we find 2 1s. We find these. We find these. We find these. So we're looking for neighbors. Can we sometimes have clashes? Yes, we can. But there should only, for every iteration, there should only be like one basin that fills up that spot if it fills up. So we also know like the highest point of the basin right now. So here it's a 0, there it's a 1, there's 2 5s, and then we just bump that up by 1. So we're looking at neighbors, and we are currently at like height 1. Then we can kind of fill up height 2. For the 0, we can kind of fill up 1 and 1. 9 we cannot fill up yet because we're only at height 2. For this basin, we can fill up 6 here. We can fill up, oh, that's not something we want to do. We can fill up this 6. Yeah, I think this might work. And then we are done with one iteration, or at least if we do these 6s here, then we're done with one iteration. Then we just do the same thing, but that means that we also need to know like the current height we're treating for every basin. So for this basin on top left, that should be 2. So we need height, we need the elements in every basin, or we can deduce height from those elements. It's just the maximum value, but no, it's not. Incorrect assumption. Sometimes we have to like bump up 2 levels, so we need an explicit height to keep track of as well. So this is something we need to do for every basin. And those dots, we are grabbing those dots out of a set of unvisited. So that would also work. I'm thinking, how should we do like the loop? Should we use a set of unvisited nodes, or should we just do a kind of a fixed point thing where we just do recursion up until we see no change in the basins up until we notice that, hey, they don't grow anymore. No, that won't work because sometimes you need to do a jump of 2. So forget the fixed point thing. Let's use a set of visited neighbors or unvisited neighbors as we were doing. Okay, I think it's starting to make sense. Or it's starting to, like, I'm seeing it as a concrete algorithm, slowly but surely. This means that we need not only the values inside a single basin, but also the current height. Height. Retreating. It's time for a type. So we have, what do we call those points? We have low points in the basin. Low points, the risk levels of low points, blah, blah, blah. Locations, let's call that locations. I'm thinking which binds more. Is it the list of int tuples, or is it a tuple of an int and an int list? I don't know actually, so let's do this to make sure. Yeah, looks like it was doing the other thing. So for basin we need locations and we need like the current height we're trading. It's really confusing. Basin is not the right word here, but let's call it a growing basin. So we make like the distinction of this is not the end result, this is a part of the calculation. It's like an accumulating value. And actually, this is what we mean with our basins. So these are the low points. We map them into singleton lists, which are the locations for the growing basins, but the current height we need as well, and that is currently the value of that single element, of the low point. Yeah. Let's call it low point. And let's return a new growing basin with locations. The single point and the height is also the single point to start with. The value at the single point. Because this is a location, not a value. Yeah, that makes sense. So let's look that value up. Ta-ta! I think we can get started with something like this. So we have 4 basins, that is correct. These are the low points and these are the values. Yeah, that looks correct. And now we can start growing these. We can start growing these by doing the lookup neighbors for every basin. Yeah. What is this? What are we doing? We're looping over a sequence or a list of growing basins, and we have a single set of unvisited nodes. And every time we grab stuff out of that unvisited set, those have to be gone for everything. But it's not really that much of a problem because we cannot have the case where a single point falls into 2 basins at the same exact time. That should not be the case. So maybe we can not worry about that too much. In my head, it's like red alarm, you will have problems here, but we just read that it won't be an actual problem, so I'm not gonna try taking care of that edge case. Okay, but so we need to do something for every basin. What do we need to do? Find all the potential candidates that are part of the growing basin by finding the neighbors of all the locations. Yeah, that's something we need to do. I'm just gonna grab, I just got rid of it, but I'm gonna stick with it. let's just grab a single basin so we can play around with it a bit. Where is my end key? There it is. So a single basin. What do we do for that single basin? We do find neighbors given the map. And we do that for every location in the growing basin, which is just the one. And we can do a collect because we don't need to keep track of which thing we started. And of course, we need... do we need locations? We need locations, not just values. Yeah, we can do that here as well. So I was a bit confused because we're doing magic with options and choose. And now I want to, instead of just a value, I want to have a tuple of the location and the value. And this option thing is kind of messing with my head, but we can do, if we find a value at a location, we can say, okay, just map over that and return the value and location. There's probably better ways to do this, or at least less confusing ways to do this. But we've been programming for, what is it now? An hour? An hour? This is the best I can come up with. So this returns a sequence of the locations and the values now. So this also changes. Now I wish I had some type signatures or some explicit types. Value is still a value. Neighbors is a bit different now. That is a sequence of locations and values. Yeah, I'm sorry for all this. It's really not understandable. I don't even understand what I'm doing. It's like it's a bit of a YOLO kind of thing, but I think it still works. We'll clean it up later. But now we can find neighbors, and now we have actual locations, which is actually something we need. Next step. Now that I see this, do we need those values right now? So these are all the neighbors we are going to take a look at. Why is the 0, 0 in there? Oh yeah, it's a 0, 1 thing. Does that make sense to only have 3 neighbors to look at? Yes, it's a corner, or it's an edge. 0. Oh, we're close. I can feel it. We're close. These are all the neighbors. Now let's intersect this with the set of unvisited nodes. So we have the set of unvisited nodes that could come into play with this growing basin. And then we need to take a look at the current height, or what do we call it? Yeah, current height. Let's maybe do that first. So let's filter out this list. Current height. Will we do this, or when do we increase the current height? That's something I'm currently contemplating. Let's do this, yeah. So the current value is, the current height is, what was it again? We're looking at location, or the pool with location 0, 1. We're currently at height number 2. Then we have these as neighbors, and there is one potential candidate, which is 0, 0. So yeah, we should end up with just a single candidate. And now we need to know, has this node been visited in the past? And that's why we are keeping track of unvisited. Uh, filter again? Sure. What was unvisited again? Locations. I don't know why we are keeping track of that value thing. Yeah, we are actually using it in line 60, so let's keep it. So now let's filter out unvisited. So is this visited somewhere else or not? If it's not, we have a list of locations that are part of this specific growing basin. Yeah, so let's call this new parts of new part of basin. Sure. A couple of things we need to do now. We need to say, okay, so this growing basin has grown. So this is actually the basin with a new location. It's the original location. And we append the new part. New part should be a sequence of locations. So let's grab the locations. Oh, this can use so much work. This code is it's making my eyes bleed even, and I have a really high tolerance for messy code. But this should update. Yeah, this should update the locations for the current basin. So 00 has entered the fray here. And it should be this one, right? Yep. And we need to do something else. We need to increase the height. By 1? Yeah, by 1. Because we're modeling time here, not height. Or like different heights from the points we visit. We're really modeling like the slow creep of lava upwards. So this is a single step for a single basin, except we need to mark these nodes as visited. So this thing we're building, this function that is calculating the next step of the growing basin or a single basin, also has to return the new set of unvisited nodes. Yes, it does. And that is just the original. I'm gonna call this the new basin. And let's call something else the new visited set. How do I end key? My end key, it's a magical button that needs a combination of 3 simultaneous key presses. I will never get used to it. But anyway. So it's unvisited. I'm using a list. Why am I using a list? I don't know. Let's keep doing it. New part of basin is what we want to get rid of. So this is the what has just gone? 0, 0, right? So this should give us everything except 0, 0. Yeah, that seems to work. And everything is already lists of stuff, so that will align nicely. I think this is the actual logic for a single. If we only were working with a single basin, this should be it. Sadly, alas, we are working with a a boatload of basins, so we're not there yet. But it's good enough to, I think, put in a function. Let's write a grow basin. Let's put that somewhere here. Plop. and this returns the new basin and the next unvisited. So it takes a basin. It also takes a height map, but that's actually like, that never changes, that height map. We don't touch it, we don't update it. So I don't need to pass this in as a function explicitly or an argument. Filtering, finding neighbors. Neighbors just need to return, or we do need to do a lookup of the value. Not only the location is relevant. We update this basin we are growing with a new part and with a new height. And we trim down the set of unvisited. Yeah, we trim down the set of unvisited nodes. Now, how do we do this for all the basins? This is where it's still not clear for me. I'm thinking that maybe a fold or something, it should work, but the only thing I'm not sure about is this. The unvisited thing has to thread through every basin we are taking a look at. So for example, if we are doing, if we're growing 3 different basins, if we remove some nodes when we're processing the first, that new set of unvisited nodes has to be the thing we take a look at during the second basin we're growing. Yeah. We could do this with writing our own kind of collection function, but I think we'll get there with a fold or something as well. So basins, fold. Let's just try it. What do we need for a fold? A function that takes a state and an element. An element is a growing basin, and it returns state. And it does this for every element. So that set of unvisited things has to be the set of unvisited nodes. Yeah. So we take a state, a growing basin, and it should return a state. Oh yeah. Okay. I see. I'm confusing stuff. Actually, do I want to do a fold? Fold is like most of the times when I use a fold, it's to reduce a list to some kind of aggregate, to reduce a list to like a maximum or a minimum or something like that. But now we're just, it's not really a fold, it's more of a map. We're mapping over basins, and those basins kind of grow, so they change. But the side effect, or the hard part, is it's not just a map, because every step inside, or every step of the map on a collection has to keep track of shared state, like the set of unvisited nodes. And I think if we do fold, that's designed to thread state through consecutive mappings. So maybe this might work. The only confusing thing is we have to figure out what we want as state, what we want as... Oh, that's actually the only question. What is state? State is the list of basins and a set of unvisited nodes? Question mark? Yeah, I think so. So I'm just gonna model this explicitly. Basins are the basins we are growing. And the unvisited nodes what is that again? A list of locations. Type world is a colon, not an equal sign. I think if we take this as a state for our folding function, we have like, in the end, this fold returns state, and the only thing we care about as an end result is this, so the list of basins. But while folding, so while we're looping over every element, we need to do something with this unvisited list. I think this might work. I have no name for this folder function, so I'm just gonna call it something obviously wrong. I'm not going to refactor the whole solution probably on this stream, but I will be refactoring the name of this function, but let's stick with it. So that was what? State basin, and it returns a new state. It's not something I do every day, F# development, and the old things get rusty real quick, so maybe not do that in production code. So then why am I doing it for advent of code? Good question. I like to torture myself. Now we're folding over every basin. So this foo function, that's actually a grow basin function with some state. It's literally the grow basin function with some state. So let's do the grow basin with growing basin. That's basin. It's a really weird word for me as a Dutch speaking person. I'm saying like basin, 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 but it looks really weird, that word. Grow basin takes a growing basin and it returns what? It just takes one basin? Cool. And it returns the updated or the grown basin and the next, yeah. Wait a second. So our fold is just doing one step of the process. Yeah, and then we need to keep doing that until the list of unvisited nodes is empty. Okay. Get with the program, yo. So it's the next basin and the next unvisited. Grow state is a terrible word, but it's slightly better. It's a minor improvement over foo, so I'm gonna keep calling it. I'm gonna call it grow state for now. So we have the next basin. We should keep track of that in basins. Let's append that to the front of the list. It's a slightly cheaper operation. Not that performance will be an issue today. I think. No. What's the problem here? Semicolon? Yeah. And I'm messing up sequences and lists. I always do that. What is that here? It's a sequence. If we do this list, it's a list. No. We also have an accessor here. Sorry for this. I'm losing track of everything. I prefer my lists eager instead of lazy. Cool. What's the problem now? Type mismatch. Expecting a sequence sequence with given a state growing basin state. The type sequence of growing basement does not match. Yeah, that's true. Oh yeah. We need an initial state. That's what it's complaining about in a very roundabout way. So just for starting, we don't have any basins in our state, and our set of unvisited nodes, that's the thing, that's this one. So if I grab this one, we should never reference it. We reference it here. We need to pass it in explicitly. So we need to pass it in explicitly here. We need to pass it in here. So state.unvisited. Tick. And unvisited is that initial list. I think this does one tick for everything. It now we need to do that until we have no unvisited nodes. Let's first run this and see how hard we crash. One tick. So this is one loop of the Dijkstra algorithm. Let's take a look at the basins we have right now. What? How can it... We do one grow? Or let's take a look at that again. We have 1, 2, 3, 4 basins we're growing in the example. And then we do just one step of Dijkstra. Yeah, it can be. In one step of Dijkstra, do we have like this many things that grow? Let's take a look at the example again. So our 2... No, we should grow with a maximum of, what was it again? 4 neighbors. So why are there sometimes 1, 2, 3, 4? 1, 2, 1, 2, 3. Yeah, actually, it could be the case. I'm gonna trust the process here. I hope I didn't make any mistakes. Has the list shrunk with something like 1, 2, 3, 4, 5, 6, 7 elements. So that should be something around 39, 38. Trust the process. Probably that's correct. So this is the Dijkstra, and we're doing this just once now. Now we just need to keep doing this, keep doing this, keep doing this. Probably until we crash. Because I just now noticed that, or I just now realized that we're doing a fold, and we are grabbing stuff out of a set of unvisited. Oh no, actually, if that unvisited list ever gets empty, things will work out. We just use that unvisited thing as a filter, and if we filter or check for elements in an empty list, that'll just give us nothing, and the process will end without crashing too badly. So if we just do this until the set of unvisited nodes is empty, I think we are done. That would be cool. Yeah, I'm like contemplating. I find it a bit shameful that I'm not that I have not written any tests today. But no, when you're searching a problem space like this, TDD, it doesn't work for me. I can't think really hard about a problem and test drive my code. I need to play around with the problem space first before that makes sense, or at least in F# I do. So let's write a recursive function that just keeps doing this until our set of unvisited nodes is empty. Don't know if there's a collection function that would help us here, and quite frankly, I don't care. We've been working at this for the better part of an hour now, so let's just finish it. What do we need? A recursive function. What are the arguments? I don't know actually, so let's not worry about that. Basins. Unvisited. Unvisited, definitely. And then we just do this thing. I'm also going to give this the inventive name next. Let's call it next state because we are returning a state type. Yeah. And if... Oh yeah, so actually we can loop over state. And if state dot unvisited is empty, we're done. Otherwise, let's do a one tick. Let's do one tick. So state basins. Let's just do a tick. I think that works. And now let's call that unvisited. Unvisited is something. That's something we need to pass through, right? And we need to do the recursive part, of course. Lol. Yeah, I'm mixing two concepts again. Let's do it again. Basins and unvisited. That state is like state for one loop. I should not be reusing that for this fixed point thing or this recursive part. Okay, so then we do one tick for all the basins or one step of growth. Why does it think basins is state? I don't understand why it thinks basins is state. Oh, probably because I have not specified the return type. Yeah. Okay, so if we have no visitor nodes, then we're done and we just return the set of basins. Otherwise, we do a tick, starting with no basins because we build those in the fold or in the grow state thing. Unvisited is something we do here. And that returns us the new state. So let's grab that. And let's do a recursive call with next state. Basins. Now that I see this, maybe it makes sense to loop over the state object itself, because we're just destructuring it here, and then when we enter the recursive loop, we're rebuilding it basically. But why is this not compiling? There we go. Does it make sense what we're seeing here? Yeah. Okay. The thing I said about passing in state through this loop, it will work, but actually those are two different concepts. One we use for the folding, so for a single iteration, and this is across generations, so I don't like mixing those two concepts. Yeah, let's keep it like this. And let's do a loop on what? Let's do a loop on especially this. We need the initial set of unvisited nodes. But where are my basins? Where are my basins? Here they are. We should not be using them anywhere. No, that's correct. Cool. Oh, silent prayer. Let's have this work first time. Troubleshooting this. That will be interesting. That will require several liters of coffee before I do that. No, it's not okay. Okay, we need a list instead of a sequence. That is a compiler error I'm very happy to fix. Let's grow our basins. We already have something called basins. It seems to finish, and it seems to finish at current height 9, sometimes 4. Why can a growing basin stop at height 4? It should never drop out of the loop. I don't really understand why that is happening. This looks weird, right? Like one base. Is this what we want? 1, 2, 3. Actually, could be. So what do we need to do with these basins? Find the 3 largest basins and multiply their sizes together. What is largest? Number of... Oh yeah, there we go, the size. Let's reread the exercise again. A basin is whatever, we just calculated those. Then the size of a basin is the number of locations within the basin. So we just count the number of locations. And that's the size. And then we find the 3 largest. Okay, so that's doable. I can do that with a caffeine depraved head. So this should map the sizes. No? What is happening? It's a list of growing basin. Oh yeah. Locations, current height. Let's get rid of current height. Growing basin. And let's map that to the locations. So that's just lists of locations. This is a list of lengths. 3, 10, 41. That does not sound correct. 3 was okay. And then things took a turn for the worse. What? How do I end up with a basin of length 41? It was not going too well. We just never ran our code, so we did not verify whether or not we were evolving towards something that was correct. Yeah, these two, they look big. That's not supposed to happen. Can we spot the problem without having to draw out? Or why are there duplicates in here? Oh, we have duplicates in here. Of course, I think what's happening. When we look at the neighbors of the basin, we look at like every individual point of the basin and look at the 4 neighbors that thing has. But it could be that that basin is adjacent to a node from several angles. So I think if we just take a look at where we do the find neighbors, the collect thing. There was a collect somewhere. Collect here. I think if we dedupe this or convert it to a set, so it only takes a look at neighbors once. That might be better already. Let's see. 9, 3, 9, 23, 15. 3, 9. It's better, but not great. What are we doing wrong here? The 3, is that a correct one? That looks very wrong. Oh no, sorry, those are the initial basins. These are the groans. 0, 1, 0, 0, 1, 0. Yeah, that looks correct. And then the other one is 1, 2, 3, size 9. That was also probably correct. But then 23, 15. Bottom right basin is 9 and we have something like 15. Is this the 15 one? Probably. What happened here? It's a basin that is covered by or walled in by only 9s. It ends with all the 9s. Oh yeah, that's something we don't do actually, right? We don't do anything with walls. What how does it even work? We should like have a hard stop when we encounter a 9. That's something we don't do yet. And that's something we identified, I think, half an hour ago already. And then I said, let's not worry about it. Well, here we are. Good job, me. You should have worried about it back then. But okay, let's worry about it now. How do we handle the 9 case? It's not part of any basin. But it also should not be... oh, maybe if we just don't use that as part of a basin, so we forget about that. But we also throw it away of the list of unvisited nodes. So we just mark it as visited and forget about it. That actually might just work. Dangerous assumptions, but you only live once. Does that mean that we can just get rid of the 9s from the get-go? I think it does. So here we have a set of unvisited nodes. These contain 9s. If we just forget about it, I think that works. And then we just look for unvisited nodes, but we treat 9s as black holes, so we will never go there. And that set will also converge to an empty set because we made it even smaller. Yeah, I'm convinced. I've just convinced myself. Let's do a to list here. So we have key values. And then we can filter out the 9s. So value should not be a 9, and then sequence except. So yeah, then we get the coordinates back again, and then we have unvisited nodes. So right now unvisited is this 1, 2, 3, 4, 5 lines of REPL output. Now we have 1, 2, 3, 4 or 3 something lines of REPL output. I think that did what we wanted to do. Let's grow again. 3, 9, 14, 9, 3, 9, 14, 9. I love it when a plan comes together. We YOLO'd a whole lot today, but it looks like it is working. Then we take the 3 largest and we multiply them together. Cool. So we take the 3 largest. So let's first sort descending. And then let's take 3. And then let's multiply. 1, 1, 3, 4. Cool, that works. And let's run that on our actual input now. This is the actual input, right? Oh no, we use the height map. That's true. So let's just do the whole thing again for input. We'll clean this up later again. It's not too bad. He said while executing the code that ends up in an infinite loop. Okay, it doesn't. Cool. Creepy number. Is it the correct number? Oh my dear. Oh lord. Oh my. We did it. We did it. I am really happy that we solved this one in 90 minutes. Typically, I mess up somewhere, and messing up somewhere in 100 lines of dense F# code with faults and stuff like that is never a good idea, especially when you have not written a single test for any of those functions, because then you start to have to do that or start to debug with a lot of print statements. But today was not that day. Lovely. Let's see. Let's quickly go over the code. So I remember what I've been doing. What did we do today? We solved part 9 or day 9 by using my basic go-to structure or data type when doing grid-based neighbor lookups, which is a map, mapping locations to values. This just parses our input into one of those maps. This is the good old strategy I use to find neighbors. Just define the deltas, whether or not you want diagonals, you can do in here. Then map those to the location you want to find the neighbors of. So apply those deltas. And then if you have a map of values, you can do a map.tryfind to grab into that map. And if you don't find anything, like we're out of bounds, that is handled nicely with an option. this option.map magic I don't usually do, but now we had, or it was one way of not only returning the value in that map, but also returning the key again, like the provided location. It's just a utility. And now that I see that, it makes no sense because we provide that as a... Oh no, yeah, it's a different thing. So we look up neighbors for this XY location, and these are the neighbor locations. Yeah. So never mind, yeah, that looks good. We're finding neighbors. Where do we use this thing? Oh, to calculate low points, yeah. Let's put those two together. Low points are points where they only have higher rated values of neighbors. So that was part 1 for today. It's already an unreadable, unholy combination of densely packed lambdas and function composition. I'm not going to refactor it today, don't worry, but no, I'm not a fan of that part. Then we have the grow basin, which does for a single basin, does like 1 tick of growing, and we used the Dijkstra algorithm, or at least we got inspired by Dijkstra, and the paint bucket metaphor, or the lava flow metaphor, where every tick of time that lava pool grows by 1, and we needed to take a bit of the height. We need to take that into account as well. This is the set of unvisited nodes that Dijkstra also uses. We keep track of both the new basin and the set of visited nodes, because we need that for all the basins. Then we wanted to do this not just for one basin, but for all the basins in our grid. And then I got a brilliant, or not so brilliant idea to do that with a fold. Yes, this one here, the fold. And that actually worked pretty nicely. And then we did a loop until we had no visited nodes. So we just loop until the unvisited set is empty. And otherwise we take one of those steps and we thread state, or we thread the unvisited nodes through the entire thing by using this fold state hacky. It's not hacky, but it's also not the most self-explanatory code, I guess. And that's it, actually. It was a fun puzzle. I think if I had ran line 106 here and it gave me the wrong solution, I would not have found this a fun puzzle, at least for a couple of hours. But yeah, I had fun. I hope you had fun. And I will see you tomorrow for the next Advent of Code in F#. Bye-bye.